Hi class, today we're going to do a midterm review for midterm 1. So first I'm going to give you a breakdown of the test. So there's going to be 10 problems, each worth 10 points. So that's 100 points in total. A few problems, not few, a few. So a few of our problems will have multiple parts. Nothing should have anything more than 3 parts, and the ones that do have parts, they're not going to be super complicated problems. It's going to be something small that should take less time than a full problem that doesn't have any parts. You're going to have 2 hours to take the test. And what's really important is when you go onto Canvas and you open the test and you start it, that's when your 2 hours start. So don't go and open it and if you're not prepared to take it, because the timer will run out and you won't be able to take it again. So be prepared and have all your stuff laid out and ready before you start the test. And the test is open note, open Canvas. Do not use any other resources. Don't talk to other classmates. Don't use the internet other than your Canvas. It's testing your knowledge and your ability to do the problems. And also, you must show work. This is really important. I don't see any work on the test. I don't know how well you understood the material, and I won't be able to grade you very easily. Okay, I think that this is a main breakdown of the test. If you have any other questions, you can email me, and I will let y'all know some more details, or if you need any clarifying questions. Also, if you cannot take the test this Friday, that's also important, it's this Friday. If you cannot take the test this Friday, I need you to email me before Friday so I can find an alternate time for y'all. If you don't let me know until Friday, there's nothing I can do to create an alternate test or let you take it at a different time. Okay, so now we're going to start the actual review. So first we started with section 3.2, which is polynomial functions. And their graphs. So we learned what a polynomial was. And we also learned the terms, leading coefficient, leading term, constant coefficient, and then just coefficient. So you need to be able to describe them and recognize them in problems. We also learned how to transform a graph. So from the basics, like x, x squared, x cubed, and so on, we learned how to take one of these basic graphs and we learned to add externally. So that's when you have something like our function and then you add a number like 3 on the outside. We learned how to add internally. So this is when we have a function and we add, something on the inside. And we also learned how to scale by a constant. So this is when we have -6 times f of x, where f of x is our polynomial. So that's the ways we learned how to do it. Adding externally shifts up and down. Adding internally, this shifts side to side. And multiplying by a constant, this stretches. Or squeezes. It only squeezes if the number you're multiplying is less than 1. So yeah, it stretches and like we'll flip graphs. So that's kind of how the beginning of section 3.2 started. We also learned how to tell what a graph is doing. As x approaches positive or negative infinity. So this is when we learned the different behaviors when it is even or odd. Okay, and remember, an even polynomial is something like this, where you have an x to an even power 2 times another number. So something like 2 to the 6th plus 3x to the 5th minus 3x. That's even because there's an even number up here. Similarly, for odd, that's something like, I don't know, negative 3x to the 9th minus 7x to the 8th plus 42x squared. This is odd because this 9 here, this is odd. Okay, and we also learned the relationship between roots of polynomials and x-intercepts on a graph. So this is really important as it helps us graph functions, because if we can find the x-intercepts and the roots, we know how, or if we can find the roots, then we know what the x-intercept is on the graph. All right, we also learned the intermediate value theorem. And the way we use this most is if you have a graph like this, where we have an A where f of A is negative, and we have a B where f of B is positive, there has to exist a C where C is 0. So that was the main way we use the intermediate value theorem, but that also means that you could have something like this. You could also just have something kind of like this, where if you know that there's some, oh, that should be yellow. If you know that f of A is like 1 and B of A is 3, there has to exist a C. Well, that doesn't actually match up. So, because this is 2, there has to exist. There we go. So that's where our C would be. A C where they equal 2 if it's continuous like this. That's another way we can use the intermediate value theorem. And then we also learned guidelines for graphing polynomials. And those are in the section 3.2 notes. I'm not going to rewrite all of them out because it's several steps. And hopefully kind of by doing the homeworks the past several weeks, you know how to use those guidelines. So then we moved on to section 3.3, which is dividing polynomials. So first, we learned the division algorithm. And this is that if you have a function p of x over d of x, we can rewrite that as q of x plus r of x over d of x, or p of x equals d of x times q of x plus r of x. So we could rewrite polynomials in this way. We also learned long division. Not long. So for example, if we had 6x squared minus 26x plus 12 over x minus 4, we would write it as x minus 4 dividing 6x squared minus 26x plus 12. And then we would multiply this by 6x, and we get a 6x squared minus a 24x. Subtract this, we'd get a 0. We would get a negative 2x. We'd bring down our 12. Okay, and then we would now multiply by negative 2. We get a negative 2x plus 8. And then we would subtract this, and we would get a 4. So this means that we could rewrite our polynomial 6x squared minus 26x plus 12 over x minus 4. This is 6x minus 2 plus 4 over x minus 4. All right, and we also learned synthetic division. All right, and so here we're going to take the same function. So now when we do synthetic division, so we have this x minus some c function, or some c number. So we take that minus c and we just write the c. So since we're subtracting 4, we're just writing a 4. If it was x plus 4, then we would have a minus sign here. All right, so then we have 6, negative 26, and 12. We pull down the 6, and then we multiply, and we get a 24, and we add, and we get a negative 2, and then we multiply, and we get a negative 8, and then we add, and we get a 4. So we get out 6x minus 2, or we get that 6x squared minus 26x plus 12 over x minus 4 is 6x minus 2 plus 4 over x minus 4. And you can see that this matches what we got up here. And it should always match if you do synthetic versus long. And we can only do synthetic when we have this x minus c in the denominator. If you have an x squared minus something or any other power of x, we cannot use synthetic. Okay. We also learned the remainder and factor theorems. And these are important because they tell us how to factor a polynomial. They give us several helpful devices in our ability to divide polynomials and find their factors. All right, so then moving forward, we have section 3.4, which is real zeros of polynomials. All right, so the first thing we talked about was the rationals zero theorem. This will be on the test. You need to understand this theorem as it's really important. All right, so then moving on from there, we had Descartes' rule of signs. So here we're looking at variations of p of x and p of negative x. And remember, variations are changes in sign. All right, and this will let us determine possible positive and negative zeros. And we need to remember that they differ by 2. So if we have something with 3 variations of sign, that means we have 3 or 1 possible zeros. We count down by 2 until you reach 0. And if we get to 1, then we can't go to negative 1 because it's impossible to have a negative number of zeros. All right, and then moving on to section 3.5, which is complex zeros and the fundamental theorem of algebra. So we talked about the fundamental theorem of algebra. Oops. As well as the complete factorization theorem. All right, and the fundamental theorem of algebra, that let us know that every polynomial has at least one complex root. And then the complete factorization theorem let us know how to completely factor a polynomial by finding that existing root, dividing it out, and then looking at our new polynomial and doing the same steps again and again and again. This is how we factor polynomials. It's very important that you understand the relationship between these two functions and how to use them. All right. We also learned that complex zeros come in pairs. So if a plus IB is a 0, so is a minus IB. And that's only for when B is non-zero. If we have just a real number, it is its own complex conjugate, so we don't have to worry about the pairs. And we learned about zeros and their multiplicity. So if we have something like x minus 3 squared, x plus 5 cubed, x minus I, and x plus I, then our zeros would be 3, multiplicity 2, negative 5, multiplicity 3, I, multiplicity 1, and negative I, multiplicity 1. And if you guys wanted to write this as plus or minus I, multiplicity 1, I would also be okay with that. You have to write it out twice since we know that they come as a pair. Okay, so then moving on, we got to section 3.6, rational functions. And this is the heart of chapter 3. This is what we've been building to, and it's kind of the most important section because it takes everything we've been working with before and it all ties together. So we learned about asymptotes and domain. And an asymptote is The main one we usually work with is vertical asymptotes, which is where we have zeros in the denominator, but we also learned about slant asymptotes, horizontal asymptotes, and then like functional asymptotes for the end behavior. And then domain is the intervals that the function can draw from. So it's basically all the points where there's not a horizontal asymptote or a hole in the graph. All right, so for example, if we have the factored function x minus 1, x plus 2 over x minus 3, x plus 5, the numerator, I'm going to write these notes in a different color. The numerator determines x-intercepts. Because our x-intercepts are 1 and negative 2, because they are the zeros of the numerator. The denominator determines vertical asymptotes. So here, they are 3 and negative 5. All right, and then for this one example in particular, the ratio of leading terms and FOILed out will give us a horizontal asymptote. All right. And then remember, the behavior near vertical asymptotes, you need to look at it from the negative and positive sides of each like cut point. You can't just look at what the function is doing as it's approaching one side. You have to look at both. So here, for 3 coming from the left side or the negative side, we would have 3 minus 1, positive, 3 plus 2, positive. And this is where it's key that we're coming in from the left side or the negative side. If we take a number slightly smaller than 3 and we subtract 3 from it, we will get a negative number. But then 3 plus 5, that's a positive number. So overall, this graph is going to negative infinity because there's one negative sign. If there's an odd number of negative signs in your little table like this, that means it's going to negative infinity. And if there's an even number of negative signs, that means you're going to positive infinity. So then if we look at the same asymptote but coming from the positive side, we'll see that 3 minus 1 is positive, 3 plus 2 is positive, and then a slightly bigger number than 3, subtracting 3 will give us a positive number, and then 3 plus 5 is positive. So this part is going to positive infinity. And then similarly for negative 5, we'll have a negative, a negative, a negative, and then a number slightly smaller than negative 5 means something like slightly bigger, and it's a bigger negative number. So like negative 6 is less than negative 5, but it's kind of bigger than negative 5. It's just a bigger negative number. So here, a number slightly less than negative 5 added to positive 5, that will give us a negative number. So all around, all the negatives will cancel and we'll get a positive. And then negative 5 from the positive side, this is a slightly smaller negative number. So we'll get negative, negative, negative. And then now if we have something slightly smaller than negative 5 plus a positive 5, this will give us a positive number. So all over, this will give us a negative infinity. So this is kind of how you'll need to approach looking at asymptotes. I saw in the homework, a lot of people were just kind of looking at it coming from one direction, not both. Or they were just looking at the end behavior and kind of guessing with their vertical asymptotes. So doing a table like this is very important. And the graph of our function is we take our -5 and our 3 and our 0 at 1 and -2. We know that. Oh, and then there's a horizontal asymptote at 1 because of the ratio of our leading terms. This you can kind of look at if you were to multiply out, you'd get an x squared over an x squared, so that's going to be a 1. So that means our graph looks like this, this, and this. All right. And then for all types of asymptotes, if we ones that continued, not continues. Okay, so if we have something ax to the n plus something and bx to the m plus something, if n equals m, then we have a horizontal asymptote at the ratio a over b. If n equals m plus 1, if n is just one number bigger than m, then we have a slant asymptote, and you'll need to use long division or synthetic division to find out which line it follows. And if n is greater than m plus 1, then we have an end behavior, not bend, end. So there was an example in our lecture videos for section 3.6 where the end behavior of our graph followed x squared, because when we used long division and we found out, we could find out what this function was. So this is common for when our leading term in the numerator is 2 or larger than the leading term in the denominator. And you can find out what that function, it's like a functional asymptote almost. You can find out what that is using long division, similarly to how we worked in our 3.6 video. So these are some of the behaviors for non-vertical asymptotes. Okay. And then also there can be a hole in a graph. So if we have something like x plus 3 over x minus 1, these x minus 1s will cancel, and so we'll have a hole at x equals 1. So this will still follow the graph of x plus 3, except there will be a hole when x equals 1. And then our domain will respect the hole there, and it will be separated out. All right, and then our last section was section 3.7, which looked at polynomial and rational inequalities. And this section is still on the midterm. It's not super prevalent. There's just going to be one problem on it. I just want to make sure you know how to run through the basics. It's not a super complicated section as long as you follow the procedure. So 1, move everything to one side. Factor. 3, find intervals based on cut points. So our cut points are zeros and vertical asymptotes. All right, for test intervals, so you'll plug in a number within the interval and see if it is positive or negative to let us know which side of the axes our graph would be on. And then 5, we're going to solve and check endpoints. Because remember, our inequalities can be strict or like greater than or less than or equal to. So a strict inequality is like just a less than or greater than. And then these have an equality. So when we have the equality included, that means we get to include 0 in our intervals. Whereas with a strict one, we do not get to include the endpoints where they equal 0. But we never get to include when we have a vertical asymptote because the graph will never reach it. All right, so that's a quick overview of everything we have done this so far in chapter 3. So good luck on the midterm this Friday.